So today we're talking about similar transformations. If shapes are similar in geometry, it means it's essentially the same shape. It's just turned and maybe a different size, but essentially the angle measures are all the same and the sides are proportional. So we're going to talk about graphing a composition of rigid motions and now a dilation. So we've done composition of rigid motions before where we said maybe we can translate it and then rotate it, or rotate it then reflect it. Now we're going to throw in dilation as one of those. Okay? So the important thing to remember about a composition of rigid motions is that the second one is the first step. So this is step one. Okay. And this one, this is step two. So there's two ways you could do it. You can do it graphically, or you can do it algebraically and then just transfer it onto the graph. So if I want to start this, doing it graphically, I'm going to plot the points x, y, and z. So x I have at coordinate 3, 5. So 3, 1, 2, 3, 4, 5. That's going to be x. And if I'm plotting y, that's going to be at 1 or negative 1, 4. So negative 1, 1, 2, 3, 4 is y, and z is at 1, 7. So 1, 2, 3, 4, 5, 6, 7 is z. So that's my original figure right there. What does this notation mean to do? That big T is 1, negative 2. What does that mean to do to that figure? If I saw that capital T, which rigid motion is that? Does that mean reflection, rotation, translation? Translation. The big T stands for translation. And this tells me my direction I'm translating. What does this 1 tell me? Is that 1 up, 1 down, 1 right, 1 to the left? One to the right, right? Remember, it's like an x comma y where you're talking about your horizontal and then your vertical. So this means I'm moving it 1 to the right, and then negative 2 means I'm moving it down 2, right? So first step is I'm translating it to the right 1 and down 2. So that's every point. So y is going to be over 1, down 2. It's going to be there now. And then z is going to be down 1, or to the right 1 and down 2. And then x, if it goes to the right 1 and down 2. Girls.
I'm sorry.
All right. And if I'm following along algebraically with this, remember we could have, instead of doing this on a graph, if I wanted to do this and just know the coordinate points, that translate 1, negative 2 means you're going to add 1 to the x's and minus 2 from the y's. Right? So if I would have done this algebraically, my x coordinate would have went to, adding 1 to the x, it would have gone to 4, minus 2 from the y. Now it's at 4, 3. Right? And that matches, that's where x prime is at. Same for the other two coordinates. Negative 1, 4. Adding 1 to the x, now it's at 0. Minusing 2 from the y, now it's at 2. That's where I would have found y prime. Same thing with z. It would have went from 1/7. This notation means add 1 to the x, subtract 2 from the y's. That's how I would have got my coordinate points without the graph, which is something you'll be able to be quizzed on. Right, but that was just the first transformation. Then we have to do the second one. What does that capital D lowercase 2 mean to do to that shape? It means dilation by a factor of, what's my scale factor? 2, right? That's good. This means to dilate by a factor of 2, which, what does it mean when I say dilate to a factor of 2? What would that do to these coordinate points? It would increase them by how much? Are we adding 2, or what are we doing to that point? Yeah, exactly. We're multiplying by 2. That's exactly what that's doing. Very good, Jim. So, to find out what the final coordinate points are going to be, I have to do the dilation on these. Right? So dilating by 2, that would have made the coordinate points I have here. On my page? Yep. Okay, so that would have made the coordinate point 4, 3. Dilating that by a factor of 2 just means doubling both those numbers. So that becomes 8 and 6. And that's my final x, or my x after 2 transformations have been done to it. Same this coordinate for y that I had previously. Just doubling both those. I'm getting my final y coordinate. And notice I'm using the points after I translate, not the original ones. Same for the final coordinate, 2, 5. Doubling those would have given me 4, 10 as the double prime. Right, and graphing those at 8, 6. Let me pull this up a little bit. 8, 6 would have been 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6. This is my x coordinate. Y would have been 0, 4. And z would have been 4, 10. 4, 5, 6, 7, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This would have been z double prime, and that would have been your final figure. Right, but if you're trying to figure out what these final vertices would have been, you can do it graphing, right? You just have to be careful about your transformations. Make sure you're doing it accurately so your final coordinates are going to be accurate. But you could also do it algebraically, remembering if you're translating, that just means you're adding to your coordinates, or you're subtracting based on whether it's positive or negative. And then if you're dilating, that's multiplying by that scale factor, whatever it is next to the capital D. Any questions on that first one?
That's the first one.
Yep, that's just the first one. Anyone need more time with that? All right, so kind of the same idea with looking at dilating by a scale factor of 3 after I rotate it by 90 degrees around the origin. All right, we can do the same thing. And relisting my points from before, I have the same coordinate points. X is at 3, 5. Right. Y is at -1, 4. And Z is at 1, 7. So, if I plot that on my coordinate plane, again, same one, so it's going to be at the same coordinate points as the other one started at. So 3 up, 1, 2, 3, 4, 5. That's going to be my x. Y is at negative 1, 1, 2, 3, 4. And z is at 1, 7. To the brain 3 on 5. Remember x on 1. This is the x, this is the 1. That's making it lowercase x. Yeah, sorry, there's a lot of x's and y's, right? Remember this axis, this is the x-axis, this is the y-axis, and these coordinates are given to us as like a lowercase x, lowercase y. So it's like 3 on the x-axis, 5 on the y. Okay, all right, and that's my original figure there. Now, I'm just going to figure out where the final figure would be using my rules for rotation and dilation that I know. So, the first step, is it dilating by a factor of 3 or rotating? Yep, that's right. Remember, the one that comes second in the pair is the first step. Now, does that matter on some of them, which order you do it in? No, not some of them. Some of them it's the same way, either order you do it in. But some of them it would matter. All right. So, if I'm doing a rotation of 90 degrees about the origin, that rule said, since we're going counterclockwise, I'm flipping my x and my y and making the y opposite signs. Okay, that was the rule we had for rotations. And you'll notice at the end of the notes I put those rules back in there along with the composition of rigid motions notes. So those will be useful for doing the homework in this section if you want to turn back to those ones. So what I'm going to have is my x coordinate, my y, and my z. What's my new x coordinate going to be if my original one was 3, 5, following a rotation at 90-degree rule? That's exactly right. I flip the order and then flip the sign of the first one. Okay. Nice job, Allie. So what about the second one? -1, 4 would become, yep, flip the order and make the first coordinate negative, and then the last one would become -7. Nice job, and that's, again, that's the first transformation on X, Y, and Z. That's why it has that single apostrophe. Right? And then we're doing, on those coordinate points, we're doing a dilation of 3. Okay, so I have my x prime that was at -5, 3. I have my y prime that was at -4, -1. And I have my z prime that was at -7, 1. If I'm dilating these by a factor of 3, what would my new coordinate pair be for x? If I dilated this by a factor of 3, yep, -5 times 3, so that's going to give me -15. And then same thing with a 3, so 3 times 3 gives me 9. And that's my x coordinate after the second transformation on it. That's why it's got 2 apostrophes on it. Same thing for my y coordinate. Multiplying both of these by 3, since they're negative, they're going to come out negative still. 4 times 3 gives me 12, and 1 times 3 gives me, yep, -3. And that's my final y coordinate. And this one multiplied by 3, negative 21, positive 3. That's my final z coordinate. And I wasn't thinking, I should have checked my scale before I graphed this, because this is certainly not going to go. This doesn't fit on my graph. So I'm going to change my scale to go by 2s. So it goes by 2s. That means my graphs are going to look like negative 5. I'm sorry. The original one, 3, 5. It's going to be my x coordinate. Z would have been at negative 1, 4. Z would have been at 1, 7. And then my final figure, after rotating it and dilating it by 3, would have been at negative 15, 9. 7, 9, 1, 2, 4. So x double prime would have been y double prime, negative 12, negative 3. 6, 7, 3. This is where double prime would have been, and z double prime would have been negative 21, 3. So that's what it would have looked like, rotating it by 90 degrees and then dilating it by a factor of 3. Sorry to change the scale there. Alright, so talking about similarity transformations, similarity transformation is just composition or just a single rotated motion and a dilation. So a reflection, a rotation, or a translation and a dilation. Right? And it results in an image that's similar to the pre-image. And again, similar just means it's essentially the same shape still. It's just in a different location and a different size. So, if we're looking at this, right, the important part on this page is this notation here. Right? If two shapes are similar, they have that little accent sign instead of the congruent symbol. So if things were equal in geometry, if it was the same shape, it was the same size, we use the congruent symbol, which is the equal sign with the accent. That means things are equal. It just means they're the same shape. This means it's a similar shape. If you just see that accent, it means it's a similar shape. So if we're talking about a star shape, we're still talking about a star shape, but maybe it's in a different location and it's a different size. Okay? What the accent means. Similar shape, not necessarily the same exact shape you started with, but it's in the same category. If that makes sense. Right. So, defining the similar transformations, we want to describe a possible similarity transformation for each pair of figures shown and write a similarity statement. So, again, the possible similarity transformation can come from a combination of a reflection, transformation, rotation, and dilation. Looking at these triangles on the left, how did I get the triangle on the left to become the triangle on the right? What had to have happened to it? A rotation and a what? A rotation and a dilation, right? Can we see that? That if I turn this triangle, it's in the same orientation and they look to be the same, but it's bigger, so it has to be dilated as well. So this one, I would say, the rotation and a dilation. And to write the similarity statement, you would say that triangle ABC is similar to, just with the accent, triangle A prime B prime, C first. Right? If there is a composition of rigid motions that makes one into the other, including a dilation now, we're going to say they're similar. So before we were saying if you could turn the shape into one another, they're congruent. Now we can also stretch the shape of the dilation. Right, so looking at the second shape, what would have had to have happened? Well, first of all, are we starting with the one on the top or the one on the bottom? The one on the top?
What are you talking about?
This one.
Oh.
Right? Are we starting with the one on the top or the bottom? The one on the bottom, right, Terry? So looking at this one, it's because I don't have the apostrophes. So I'm going to the one with the apostrophe. What would have had to have happened to make this one into this one? A dilation. Okay, I would have had to make it smaller. And what would have been the scale factor if it's getting smaller? What would I have known the scale factor would have been between if it's getting smaller? What two numbers would the scale factor have been between?
Well, 1 and
Not 1 and -1. So we don't talk about negative.
0 and 1.
Right, 0 and 1. Remember, if I'm getting smaller, that means it's a fraction. That's my scale factor. Good job, Terry. So a dilation would be one movement, but how do I get this shape to map on the other? What's that? Well, you see the Z is in the bottom here when it's on the top here. Right. It's a reflection over this line and a dilation. Now let me ask you this too. With either of these transformations, would it have mattered which order they happened in? No. Okay. So this one is reflection and dilation. And then again, to write the similarity statement, if it's not a triangle, you're just using all the letters. So we have X, or W, X, Y, Z is similar to W, X, Y, Z prime. And now, if you want to be exact with your transformations, you can't figure that out unless you actually know some side lines. Right? You can figure out what the scale factor is. Okay, questions on this so far? Okay. So determining whether some things are similar or not. Looking at this application problem, we want to know, can an artist copy her sketch to cover an entire wall measuring 15 feet high by 20 feet wide, so her wall mural is similar to her sketch? Explain. So, we want to know if she can expand or duplicate her original painting to cover a 15-foot by 20-foot wall. So the first thing we have to do with a problem like this is we first have to be talking about the same unit of measurement, right? Here we're comparing feet to inches, so I want to get either both of them in feet or both of them in inches. Okay. So if I am saying, let's convert the walls, which are feet, into inches, how would I do that? How would I turn 15 feet into inches?
You're saying how would you turn feet into inches?
Yep. So let's start with how many inches in a foot? Okay, if there's 12 inches in a foot, how many are there in 2 feet? How many in 3 feet?
36.
So what are you doing to get those numbers? You're adding 12 every time, right? Or you're multiplying, right? So like 3 feet times 12 inches, get 36 inches. If I want to convert feet to inches, I need to multiply by 12, right? Since there's 12 inches in every foot. So I have 20 times 12 and 15 times 12. That's going to give me, what there, 240, 2400, I want to say. Right, and 15, 12, 180. Right, so now we know our new dimensions. We have 240 inches by 180 inches, and originally her sketch was 11 by 14. So I'm not drawing the scale, but how would I be able to determine whether or not her picture would fit evenly into that? How could I use those numbers? Well, how would I know how many of these I can set side by side? So like, we're trying to see like if I can expand this, right? So really the question is, does it fit evenly into 240 by 180 dimension wise? If I want to know if these fit into one another, I have to see if 240 divides evenly by 11 inches, or if 180 divides evenly by 14 inches. And if they do, it should be the same exact number, and that'll be, well, it is proportional. It has a scale factor that would multiply it to be that bigger, right? Remember when we were talking about dilations before, we said that the ratios of sides, like if this side is 5 times longer than the original bottom side, the other one has to be 5 times longer. So if I do 240 divided by 11, that gives me 21.81 repeating. And if I do 180 divided by 14, that gives me 12.857 and some change. So, does this picture fit evenly? No. It's not going to fit evenly either. So yeah, I would say, how would I phrase it? I would say her painting would not scale to fit the wall. So if you want to know if something would scale, that has to divide evenly the same amount of times. Alright, so identifying similar circles. So there is nothing to write on this page, but I put it on here because you may be asked about a proof that, and there's similar proofs to this one. Write a proof that any two circles are similar. Okay? So it's a fact in geometry that circles are similar shapes, right? Just because if I have a circle and I have another circle, it's related to, they're related to each other because one's just bigger size, a different size, smaller size, right? So all circles, since by definition they're a circle, are similar to one another. And we just need a proof that says so. Okay? And the proof follows kind of like the work we did before. We just have to name the transformations that would map one circle onto the other one in any case. Right? So this is just talking, so they use variables to just talk about like in general, right? So given any circle with any radius and another circle with another radius, we want to prove that the two circles are similar. So to do so, we could translate one circle onto the other so that the centers overlap, then find a scale factor that stretches the one circle onto the other, okay, is what this is saying. Does that make sense? All circles are similar because you can map a circle onto another circle and stretch it to become the same size as the other. Okay? Can you give me another shape that is similar? That all shapes of the kind are similar? What's that? Not necessarily a hexagon, but as long as it's, there has to be a condition on that hexagon. Well, can anyone think of another shape? Not necessarily a trapezoid, because you could have the sides at different angles out. A square, right? All squares are similar, right? Because by definition, the square has all the same sides, right? Your hexagon would have been, all of hexagons would be similar if they all had the same side lengths, right? So all squares are similar because you can put a square onto the other square and stretch it till it becomes the square you want. So that's kind of the proof, or the idea of thinking with these proofs. That's just the math language that goes with it. Okay. So those are my notes for today. At the end of this, you'll notice this concept summary. Okay? It means for things to be similar if you can map one onto the other and dilate it. Okay, so that's another tool in our toolbox for changing shapes. And remember, this notation, this little accent symbol, that means similar to. So it's the same shape, just different size. And then this last page on your notes, these are those transformation rules for coordinate points that'll come in handy if you don't remember them. So if you want to rotate, those are the rotation rules, and reflections, those are the reflection rules.